how molecules actually are pretty simple in how they make their three-dimensional shape. You can imagine each of the charge clouds, or the density of electrons, as a balloon that's repelling each other. And if you think about it that way, you'll get the answer right virtually every time. And so electrons just want to get as far away from each other as possible. And that's going to ultimately dictate its final molecular shape. So I want you to paste this link into your browser, and I'm going to walk you through how to use this. This is a really helpful tool in helping you visualize and practice with this. It's nice to just have it up when you're building some of these early structures. Okay, so hopefully you're able to pull up this simulation. It's really wonderful, and it helps you get a sense for three-dimensional structures and how they form. So this is the screen you'll see when you first open it up. So you've got this example molecule starting with really the simplest molecule. If you click and left click and hold and move around, you can actually drag this molecule in 3 dimensions and see what it looks like. Down here in the bottom left where it says name, you can click the molecule geometry and electron geometry. Molecule geometry is what we've been talking about, so it'll tell you what the shape of this thing is. And then over on the right where it says bonding or lone pair, you can click any one of these and it's going to add that to whatever the structure is that you have. And so if I wanted to tack on, let's say, a lone pair to this system, now I've got a molecule that has 3 charge clouds, 1, 2, 3, but only 2 bonds. We'll remember back from earlier video that this would give us a bench structure, right? I can take this off too, so we can have to force ourselves to think about this a little bit. You can also click down here and show the bond angles, which can be nice. Let's tack on another lone pair. What does this molecule look like? Hopefully you have some general intuition. You're thinking about, oh yeah, I've seen that before. That's water, right? Water looks exactly like this, where you'd have hydrogen, hydrogen, oxygen, and then 2 lone pairs. Those lone pairs push these bonds down, they distort it, and that should give us another molecular geometry of bent, right? Yep, and that's what we see. We could, to remove a lone pair, I just click on the red X. I can get rid of that. Maybe I want to toss in another single bond. What does this look like? Well, this is NH3, or ammonia, and we know this is 4 charge clouds, but 4 charge clouds, 3 bonds. And we know that's a trigonal pyramidal shape. Yep, and our guess is right. We can get rid of this lone pair. We can tack one of these on. What does this look like? Well, that's our tetrahedron, so that's methane, just like that. We could get rid of one of those bonds, and we could, well, we could keep that there, and we could tack another one of these on here. We get the seesaw geometry. That really helps visualize the seesaw. So there's the seesaw. I don't know if I can get it to rock. No, not really, but you get a sense for what that seesaw looks like. Tack another bond on there. Now I've got that square pyramidal geometry. It's easier to see it from this dimension. So the square pyramid, we've got the 4 atoms here that form the square at the bottom, and then if you connected them all to the top vertex, we'd have this square pyramidal. We could pop, we can't add any more single bonds here because we're at the maximum. We've got all 6 of our slots filled, so we got to get rid of a lone pair if we want. That'll be this trigonal bipyramidal shape. Trigonal bipyramidal, easier to look at when it's like this. The trigonal comes from this triangle right in the center. Each of those at 120 degrees relative to each other, and then 90 degrees below. So show these bond angles here. So 90 there. Let's see if it'll show me the 120. Yep, and then 120 there. Perfect. What else are we missing? We can tack another one of these on there. What is this shape? That's our octahedron. That's the really high symmetry. 6 bonds, 6 charge clouds. Let's see, are we missing anything? Let's get rid of that. Let's get rid of that. Let's tack 2 of these on here. Now we've got that square planar arrangement that we talked about at the end. So I think it's really helpful for you to practice and visualize with these things. So I'd play around with this as much as you can. Alright, with that simulation still open, I encourage you to walk through a couple examples that I go through here. Pause the video and try to work them on your own, and then unpause it and see how I've worked it. So we're going to work with BR-F5 first. So pause the video here, get a piece of paper, and see if you can sketch out the steps. Okay, so I just drew up the Lewis structure. We should have lots of practice with this. So this one's pretty straightforward. So I counted 42 valence electrons on the BR-F5 molecule. I then looked at the bromine as the central atom with the lowest electronegativity, put that in the center, arranged 5 of these fluorines as single bonds out here. That 5 bonds is 10 electrons, so I subtracted 10 from 42. That gave me 32, which I distributed across the peripheral atoms. That was 30 electrons. I had 2 left over, which I added to the center of the bromine atom here. So let's count up how many charge clouds and how many bonds we have. We've got 1, 2, 3, 4, 5 bonds, but we actually have 6 clouds if we count that lone pair. So 6 clouds and 5 bonds is going to give us the square pyramidal geometry. Square pyramidal. And so let's try to sketch that out as best we can, because this here is just the Lewis structure. That's 2D. That doesn't tell us what the 3D structure is. So the actual 3D structure would look something like this. Bromine here, I've got one of the fluorines in the plane. I've got a fluorine out here, and I've got one fluorine coming out at me. I've got another fluorine. I'm going to color these in just to be clear, coming out at me, and then another one back in the plane. And then my lone pair would be sitting down here, which I could draw just like that, or I could be more explicit and draw it like that, just to be clear. And so remember that the square is here. I don't know why that changed colors. That's where the square comes from, and then the vertex is all pointing up there. That's the square pyramidal shape that we're talking about here. So on a quiz or on an exam, if I asked you for the 3D drawing, I'd ask you for this, except you don't need all these purple lines. You just need to show the green shapes using the hash marks, the wedges, and the straight lines to indicate whether things are coming into or out of the screen. So let's look at a second example. This is xenon difluoride. Let's pause the video and see if you can work through this in the same sort of system or process that we used in the previous. Alright, so I've got the Lewis structure drawn up here. Counted 22 electrons. It took 4 to make these 2 bonds. I distributed those 18 around the fluorine first. That only accounted for 12 of them, which meant that I needed to get rid of 6 more. So in this case, 6 full electrons went around the xenon atom in the center. So let's count up how many bonds and how many charge clouds. We've got 2 bonds, and we've got 1, 2, 3, 4, 5 clouds associated with this. So 5 clouds. Let's draw this structure 3 dimensions. So that would be xenon and, changed color on me. Xenon, fluorine, all in the same plane, and then I would have all of my lone pairs as 3 clouds. This would be a completely fair representation. I should draw these to be explicit. All the lone pairs. You'd be done if you called it this. You could also represent it, just if you wanted, by showing the charge clouds explicitly here in this sort of triangular plane in the center. So we would call the shape of this thing linear.